Welcome, friends. I'm glad you're here. Tonight we'll gently explore dark energy and how it accelerates the universe's expansion, what it might be, how we know, and why it matters. If this brings you calm or curiosity, please like, subscribe, or share. Thank you. Galaxies do not rush like birds through air. Rather, the air between birds becomes more air, and the distances widen with no wind, no pushing hand. Light from far islands of stars arrives, stretched its wavelengths, drawn longer by the growth of space. In simple terms, recessional velocity grows with distance, a proportionality often named the Hubble-Lemaitre law. And in this plane relation, the universe discloses the most understated motion imaginable, the stillness that moves everything apart. The telling stays even and unhurried. A spectrum is a sentence, and its letters are lines from familiar atoms: hydrogen, calcium, oxygen, iron. In nearby laboratories, those lines sit at fixed wavelengths. In galaxies 1 billion light-years away, they appear shifted to the red, as if a violin note has deepened by the width of an evening. The fact holds redshift increases with distance, and the scale factor, an unobtrusive AT that measures the size of the universe, quietly grows with time. A lesser-known detail settles into the room like pale ash through every cubic centimetre of space. On average, hundreds of ancient microwave photons drift, faint survivors of the first light now chilled to about 2.7 Kelvin. Each one stretched to millimetre lengths, each one a souvenir from a time when the whole sky is a bright fog. They bathe metal skin glass deserts, oceans, and the back of the eye with the same thin radiance. No permission is asked, no boundary is crossed, and nothing feels warmer for their presence. The mind, searching for edges, finds only more room. The first soft irony rests here: the expansion that governs everything feels like nothing. Local rooms ignore it. Atoms hold their shapes. The solar system keeps its measures. A galaxy's self-gravity gathers stars so tightly that the universal drift cannot pry them apart. Between galaxies, however, the same expansion writes itself with patience into the vast dark, and distance obeys. A second irony follows: the messenger of this widening light loses energy, not by friction, for space offers no medium, but by generosity. The wavelengths give way to length, and the colour slides toward red only because the page beneath the ink is enlarging. No hand touches the note, but the note descends. A third irony closes the small trio: the universe speaks more clearly the farther one looks back. Dimmer is older, older is nearer to the beginning, and yet the beginning hides more completely the closer one draws to it. The present section stands at a quiet threshold where observation becomes idea, and idea remains subordinate to observation. Nothing supernatural is proposed, nothing theatrical is required. Redshift surveys map great arcs of galaxies. Pencil-thin beams of radio waves pass through intergalactic hydrogen like rain through smoke. A camera staring for days gathers each shy photon, and the image that forms shows thousands of distant systems occupying a space perhaps no wider than a grain of sand held at arm's length. In such a frame, expansion becomes visible not as motion but as architecture. Filaments thread the dark, clusters bead the threads, voids open like rooms that never receive furniture. Over time those threads lengthen, and the rooms enlarge while the furniture remains where gravity insists. The observer's voice remains absent. The scene explains itself by existing. A quiet mystery waits at the centre of this simplicity. The law is plain, space expands, and the measure is plain lines redden with distance. Yet the cause of the late-time acceleration discovered when certain standard candles arrive too dim to fit a merely coasting universe refuses a clear portrait. If the accelerator is vacuum energy, it behaves like a constant pressure with negative sign and equation of state parameter near -1. If it is a field that changes, it leaves almost no trace of its change. If it is a gentle failure of gravity at the larger scales, it copies vacuum energy's handwriting so closely that confusion becomes the default. The name dark energy adds as little as possible. It describes only that something steady or nearly steady fills space and pushes it to grow faster, and yet even that verb pushes misleads because there is no surface to press. To settle the mind, an analogy drifts in quiet and incomplete like a fabric that stretches not from its edges, but from within every thread space extends at every point, and the threads of light pulled through lengthen accordingly. The analogy remains ordinary and fails in some corners, yet it keeps the peace of the picture without overspeaking. One fact holds the ground underfoot. Spectra recede with distance in a manner consistent with an expanding metric. The fit to the data builds the scaffolding for all that follows. Another more delicate detail rounds the corner among those ancient microwave photons is a faint pattern, minute temperature variations as small as 1 part in 100,000 imprinted when the cosmos is young and dense. They are not a topic of this moment, but their mere presence in the background air of thought cools the room and confirms that expansion is not rumour. The mind leans forward again and finds the mystery unchanged, which is its own kind of answer. No drama breaks the hour. The contemplative pace remains, on a table of scales that ranges from the width of a sodium line to the span between clusters. The increase of the scale factor writes a single unadorned sentence: distances grow. The sentence does not hurry. It does not argue. It sits beside a second sentence that future sections will unfold. The growth itself now accelerates. Together they compose the quiet structure of fate. For the present, the telling stays strictly here at the doorstep, where observation meets idea, where redshift whispers an accounting of distance and time, where light already halfway here from 1 billion years ago arrives, with its colour eased toward crimson, and where the room remains untouched by any sense of motion. Expansion is the only motion that does not move. The sky, even when overcast or city-lit, carries the same relation through the night. It neither insists upon attention nor hides from it. A listener falls still, and space grows. The clock beside the bed advances by seconds. The cosmic clock counts in factors of the scale. Both keep true in their own domains, and neither notices the other. The narrative neither concludes nor begins. It simply allows the universe to continue doing what it already does. Lengthen its quiet intervals, soften the colour of distant fires, and permit more emptiness to exist between things that remain themselves. Here, in this patient widening, the role of dark energy waits just ahead, like a breath held for a long time, already present by effect, and not yet named in detail, while the night accepts its own measure and does not resist. The constant in the void emerges first not in the sky, but in the mathematics of general relativity, a term that seems almost optional in Einstein's original equations. It appears as a gentle addition, a steady background pressure, the cosmological constant introduced to allow a universe that neither expands nor contracts. At the time, the prevailing thought assumed the cosmos must be static, as the stars seemed fixed in their arrangements. Yet the constant is not a force in the usual sense. It is a property of space itself, a density of energy that does not dilute as the universe grows. When Hubble's observations showed galaxies receding, the idea of a static cosmos dissolved, and Einstein famously abandoned his constant, calling it his greatest blunder. Decades later, when the late 20th century revealed not only that the universe expands, but that the expansion accelerates, the same constant returned no longer a mathematical convenience, but a necessity to describe what the cosmos insists on doing. The fact rests quietly in the simplest model. This dark energy can be represented by a cosmological constant, with an equation of state parameter exactly equal to -1, meaning its pressure is negative and equal in magnitude to its energy density. This single property allows it to work against gravity's pull on large scales, not by pushing in any ordinary way, but by remaining constant as space increases, so that the total amount of this energy grows with volume. A lesser-known detail rests in the precision of its measured value. Current observations place its density at roughly 70% of the total energy content of the universe, leaving only about 30% for matter, most of which is dark. This proportion is so stable in our epoch that it shapes not just the far future, but the present architecture of the cosmic web. A quiet mystery lies in how small the value actually is compared to what quantum field theory might suggest. If the vacuum has energy, naive calculations predict a density, some 120 orders of magnitude larger than observed, a discrepancy so severe it dwarfs any other known mismatch between theory and measurement. The first soft irony is that this tiny number dominates the large-scale fate of everything. The second irony is that its presence is not felt in the places where life dwells. No atom in a hand feels its influence, no orbit is perturbed by it, and yet it dictates the expansion of billions of galaxies. The third irony is that Einstein's so-called blunder becomes an essential truth, as if a dismissed note in a score later becomes the quiet refrain that holds the whole composition together. Observations draw the constant into the real sky through the behavior of distant light. When astronomers measure the brightness of standard candles and find them fainter than expected for a decelerating universe, the simplest fit to the data is an accelerating expansion, driven by a constant term in the field equations. Large-scale structure surveys show that without such a term, the distribution of galaxies and the observed anisotropies in the cosmic microwave background would not align with what is measured. In this way, the constant leaves its fingerprints in multiple independent records, each recorded in a different medium, in the deep redshift of supernova light, in the statistical clustering of galaxies in the minute ripples, frozen into microwave radiation from the time when the universe was only about 380,000 years old. The image that forms is slow to appear, not unlike the way a long-exposure photograph gathers starlight. Each dataset is a layer, and together they outline a cosmos where the constant is not an adornment but a foundation. There is no sound to its action, no vibration, no detectable particle that carries it. It is only the shape of the equations and the fit to the data that reveal it. The mind may search for an analogy and find an incomplete one, a perfectly still reservoir that when its shoreline expands is somehow instantly filled, so that the water level does not drop no matter how far the shore recedes. The analogy falters because water can flow and space cannot yet. The image offers a hint of how this energy density remains unchanged, even as there is more space to hold it. The fact that the cosmological constant works identically in all directions and at all locations leads to an absence of preferred places in the universe's expansion. There is no center from which it originates, no boundary to which it tends. A quieter detail is that in models without it, the universe's age calculated from its expansion rate is too short to match the ages of the oldest stars. Adding the constant resolves this mismatch, bringing the timelines into agreement. The mystery remains why it has the particular value it does now when the densities of matter and dark energy are of the same order, a coincidence that would not hold in most epochs of cosmic history. Some call this the coincidence problem, though the term explains nothing and offers no resolution. The constant's role is everywhere, yet its influence on human scales is effectively zero, a fact that permits life and structure to persist unbothered. The constant's dominance on cosmic scales means that over billions of years, the recession of galaxies not bound to our local group will accelerate, until they pass beyond the cosmic event horizon, their light forever unable to reach us. In this way, the constant writes a slow separation into the future, not with violence, but with inevitability. This future is not a matter of local choice or technological intervention. It is the outcome of a simple term in the equation, small in value, yet boundless in effect. The narrative remains unhurried, for the constant works without haste. Even now, while the Milky Way rotates and stars form in spiral arms, the background expansion is subtly increasing like a tide so vast that it can only be measured by comparing the shoreline's position over many lifetimes. In the end, the cosmological constant is both the simplest and the most enigmatic representation of dark energy. It fits the data as cleanly as any model, yet it leaves unanswered the questions of origin, magnitude, and meaning. It is as if the universe carries a steady breath within itself, a pressure that does not change with age, ensuring that the space between the galaxies will always have reason to grow. Here in the stillness of equations and the quiet agreement of observations, the constant rests, shaping the cosmos without movement, without sound, without end. Light from dying suns travels across the deep fabric of the universe, carrying the signatures that reveal its own distance and the history of the space through which it has passed. These suns are not like the ones we see each day. They are type IA supernovae, the brilliant ends of stars in binary systems, where a white dwarf quietly pulls matter from a companion until it reaches a precise limit, triggering a thermonuclear explosion. This limit set by the Chandrasekhar mass at about 1. 4 times the mass of the Sun ensures that such supernovae release nearly the same intrinsic brightness every time, making them standard candles. By comparing their known luminosity to their observed brightness, astronomers can calculate their distances with remarkable accuracy. In the late 1990s, 2 independent teams measured dozens of these supernovae in distant galaxies, expecting to find that the expansion of the universe was slowing under the pull of gravity. Instead, they discovered that the supernovae were dimmer than predicted, indicating they were farther away than they should be in a decelerating universe. The conclusion, checked and rechecked, was that the expansion was not slowing but accelerating. The fact stands clear. Type Ia supernovae observations provided the first direct evidence that dark energy exists. A lesser-known detail rests in how these measurements required a precise understanding of cosmic dust and its effect on light. Dust can redden and dim light, mimicking the signal of acceleration, but careful calibration across different wavelengths confirmed that the dimming was not due to dust alone. A quiet mystery endures why this acceleration began when the universe was about 9 billion years old, long after matter had dominated the cosmic energy budget. The first soft irony is that the very objects marking the violent deaths of stars became the most reliable beacons of the universe's gentle large-scale motion. The second irony is that something so cataclysmic as a supernova can serve as a tool for measuring something as smooth and uniform as the expansion of space. The third irony is that while the light from these explosions can outshine an entire galaxy for weeks, the message it carries is one of gradual change across billions of years, almost invisible without careful comparison. Observing these supernovae requires patience and coordination. Telescopes on different continents and in space work together to catch them in the act, measuring their brightness over time to produce light curves that are then compared to nearby examples. From these light curves, distances are calculated, and when plotted against redshift, the curve bends not downward, as a decelerating universe would demand, but upward, showing the unmistakable signature of acceleration. The implication is profound. Some form of energy with negative pressure must be filling space, counteracting gravity's slowing influence. In the standard cosmological model, This energy is described by the cosmological constant, but alternative ideas such as quintessence or modifications to gravity remain under investigation. The supernova data alone cannot fully distinguish between these possibilities, yet they set a firm baseline that any theory must match. A delicate detail is that nearby supernovae observed with the same techniques confirm the calibration of the brightness scale, ensuring that no hidden change in the nature of the explosions themselves is responsible for the effect. The light of these ancient events has often travelled for billions of years, beginning its journey when Earth was still home only to simple single-celled organisms and arriving now to be caught in the mirrors and detectors of our observatories. In this sense, every data point on the supernova plot is also a time capsule, showing the universe not as it is but as it was when the light departed. The mystery of dark energy deepens when these time capsules are compared across cosmic history. They show a universe first dominated by radiation, then by matter, and now by dark energy. This shift in dominance is not sudden, but it is decisive, and it suggests a future in which dark energy's influence will grow without bound. The analogy of a runner slowing down before speeding up again is tempting but incomplete, for the cosmos does not have an external track or a finish line. It has only its own internal clock, and the ticking of that clock is altered by the very expansion it measures. The irony of the situation is that while these supernova mark endings, their role in our understanding marks a beginning, the beginning of a new era in cosmology, where the fate of the universe is seen as tied to a component we cannot see, touch, or directly detect. The observational programs continue adding more supernovae to the record, refining the curve testing for any sign of deviation from the simple picture. Future telescopes will search for supernovae even farther away into the epoch, when the first galaxies formed, hoping to map the onset of acceleration with greater precision. In the meantime, the data we have already draws a clear and steady picture. The scale factor of the universe is not just increasing, the rate of increase is itself increasing. This is the kind of change that is imperceptible on human timescales, but inexorable on cosmic ones. The light from these explosions is often compared to a lighthouse beam, but this metaphor misses an important truth. The beam does not sweep across the dark. It remains fixed, and the shoreline the observer drifts away. In this drifting, the message of dark energy is carried not in the violence of the explosion, but in the space the light must cross to reach us. That space is not empty. It is the very medium whose growth is being measured. This interplay between the finite lives of stars and the infinite stillness of space gives the supernova observations their unique place in cosmology. They are both fleeting and permanent transient events that leave a lasting imprint on our understanding. The patience required to interpret them mirrors the patience of the universe itself, which unfolds on timescales far beyond our own, yet leaves clues small enough to be gathered by human instruments. In this way, light from dying suns has become one of the most important witnesses in the quiet trial, where the universe reveals its true expansion. It testifies without voice, without urgency, and without bias, leaving us only to listen to the faint shift in its colour and the slight dimming of its glow, and to read in those signs the ongoing acceleration of all that exists. The shape of infinity is traced not in a single image, but in the combined weight of multiple measurements, each pointing toward the same quiet conclusion. On the largest scale, space is remarkably close to flat. This statement in cosmology has a precise meaning. It refers to the geometry of the universe as described by general relativity, and measured through the relationship between distances and angles. In a flat universe, parallel lines remain parallel. The sum of the angles in a large triangle adds to 180 degrees, and the paths of light are not bent by curvature, except where mass intervenes locally. The fact drawn from high-precision measurements of the cosmic microwave background, particularly by missions such as WMAP and Planck, is that the spatial curvature parameter is extremely close to zero within a fraction of a percent. This observation alone might suggest a balanced cosmos, but in the context of an accelerating expansion, it carries a deeper implication. If the universe is flat and expanding faster, then there must be a dominant energy component with properties like those of dark energy. A lesser-known detail is that the geometry is determined not just by the distribution of matter and energy now, but by the total energy content integrated over cosmic history. Light from the early universe frozen into the microwave background, when it was only 380,000 years old, carries imprints of the sound waves that once rippled through the hot plasma. These ripples have a characteristic scale, the sound horizon, which becomes a standard ruler against which cosmic geometry can be measured. The positions of the acoustic peaks in the microwave background's power spectrum match exactly what would be expected in a flat universe, dominated today by dark energy and dark matter. A quiet mystery remains why this flatness persists, despite the dynamical evolution of the cosmos. Without inflation in the very early universe, any small deviation from flatness would have grown over time, leading to a pronounced curvature today. Inflation solves this by stretching space so rapidly that any initial curvature is smoothed away, but the coincidence that we live in an era when dark energy and matter densities are of the same order still sits unexplained. The first soft irony is that we can speak about the shape of the universe without ever leaving our small planet inferring its geometry from patterns in ancient light. The second irony is that while the universe is flat on cosmic scales locally, it is anything but. Galaxies curve space-time around them, stars bend light into arcs, and black holes fold geometry into horizons from which nothing returns. The third irony is that knowing the universe is flat does not tell us its size. It could be infinite or it could be finite, but wrapped in a topology beyond our current detection. Observationally, flatness means that the rules of Euclidean geometry apply on the grandest scales we can see, yet this geometric calm does not translate into a static reality. The expansion continues, and dark energy's presence ensures that it will not stop. The measurement of flatness relies on an interplay between theory and observation so delicate that any significant error in one could mislead the other. Yet independent checks using baryon acoustic oscillations in the distribution of galaxies confirm the same picture. These oscillations, fossilized from the same sound waves that shape the cosmic microwave background, leave a preferred clustering scale of about 150 megaparsecs acting as another standard ruler. When measured in galaxy surveys, the angular size of this scale again points to a flat geometry in a universe where dark energy dominates. A subtle detail is that flatness does not imply uniformity in all directions. The universe is statistically isotropic and homogeneous, meaning it looks the same in every direction and at every location on large scales, but smaller scale structures vary enormously. Yet even these structures, from galaxy clusters to cosmic voids, are embedded in the flat background metric. The mystery of why the total energy density is so precisely equal to the critical density needed for flatness remains one of the most persistent in cosmology, with inflation providing a plausible but still incomplete answer. In a flat universe with dark energy, the fate is determined not by geometry, but by the nature of that energy. If it remains constant, the expansion will continue to accelerate indefinitely. If it changes over time, the geometry could still remain flat while the dynamics alter in unforeseen ways. This distinction underscores how geometry and expansion rate are related but not identical. The analogy of a perfectly level road stretching into the distance offers a partial sense of flatness, but here the road is expanding beneath your feet, and the rate of expansion is increasing with time. The road's levelness does not prevent the horizon from receding faster and faster. In this way, the shape of infinity is not a static thing, but a dynamic balance maintained across cosmic epochs. The fact that this balance is observed today gives us a clear snapshot of the current universe's parameters, but it also anchors our models of its past and future. Precision measurements of the microwave background's polarization patterns add another layer of confirmation, revealing the subtle effects of gravitational lensing and reionization while still supporting the flat model. The irony here is that the most ancient light stretched across the entire sky tells us more about the universe's shape than any direct measurement of distances in the local cosmos ever could. That ancient light, now cooled to microwaves, has been in flight for 8 billion years, and in its faint variations lies the geometry of everything. As it arrives, it's absorbed by radio antennas and detectors chilled to near absolute zero, its message transcribed into maps that, when analysed, yield the curvature parameter as nearly zero. This is not an absence of curvature in all senses, but the absence of net curvature across the observable universe, an equilibrium maintained on the grandest scales. The persistence of this condition alongside an accelerating expansion sketches the paradox of a universe that is geometrically calm yet dynamically restless. The flatness gives no hint of the eventual isolation of galaxies from one another, no hint of the event horizons that will define the far future, yet it is the geometric stage upon which all of these outcomes will play out. Standing here in thought at the intersection of geometry and expansion, we see the universe as a vast level plane in which every point is moving away from every other point, not because of a slope, but because the plane itself is stretching. The shape of infinity is not bent, but it is in motion, and in that motion the role of dark energy is already inscribed. Patterns in the cosmic web emerge from deep surveys of galaxies, revealing a structure that spans hundreds of millions of light years. Vast filaments of galaxies thread the observable universe, meeting at dense knots, where clusters form while between them lie immense voids almost entirely empty of matter. These arrangements are not random. They are the fossil record of initial density fluctuations amplified over billions of years by gravity. In the early universe, slight variations in density seeded by quantum fluctuations during inflation grew, as matter fell into overdense regions, forming sheets, filaments, and nodes. Dark matter, invisible yet dominant in mass, provided the gravitational scaffolding upon which galaxies formed, guiding them into the network we observe today. The fact that these structures match predictions from simulations based on the lambda cold dark matter model confirms our understanding of large-scale formation, but dark energy alters the pace at which the web evolves. A lesser-known detail is that dark energy suppresses the growth of structure over time. In a universe without it, gravity would continue to draw matter together, slowly building ever larger clusters. With dark energy dominating the energy density, the expansion accelerates, increasing the separation between structures and reducing the rate at which new ones can form. The quiet mystery lies in the timing. Acceleration becomes significant only after the web has reached maturity, allowing galaxies and clusters to form but ensuring they will grow no larger in the far future. The first soft irony is that the universe becomes most dynamic in its large-scale architecture just before it begins to settle into a slow freeze. The second irony is that the web, though immense and complex, is fragile on the scale of cosmic time. Its visible connections will eventually stretch until they disappear beyond our horizon. The third irony is that the voids which hold almost nothing expand the fastest, and will one day encompass almost everything. Observations from surveys such as the Sloan Digital Sky Survey map these patterns in detail, showing filaments hundreds of millions of light-years long and voids tens of millions of light-years across. Baryon acoustic oscillations imprinted on the distribution of galaxies provide a consistent standard ruler, linking the large-scale map to measurements of cosmic geometry and the expansion rate. In simulations, the cosmic web evolves like a slow-motion dance, with filaments thinning and nodes becoming more isolated as dark energy's influence grows. This process is already underway. Galaxy clusters that are not gravitationally bound to us are receding, and their light is being redshifted toward wavelengths that will eventually render them invisible. A subtle detail is that the distribution of voids can also be used to probe dark energy. The shapes and sizes of these empty regions change over time in a way that depends on the expansion history of the universe, offering an independent check on supernova and microwave background results. The analogy of a sponge held under gentle tension captures a fragment of this reality. The filaments and nodes are the denser parts of the sponge. The voids are the air pockets, and dark energy is the invisible stretching that enlarges the whole without altering its fine internal texture immediately. Yet unlike a sponge, the cosmic web is not elastic. Once structures are pulled beyond one another's gravitational reach, they will never reconnect. The mystery deepens when considering the fate of this network. In trillions of years, the accelerated expansion will leave each gravitationally bound system, such as the local group isolated in an ocean of darkness, its filaments and neighboring clusters gone beyond the cosmological event horizon. This future is not visible to the eye in any present observation, yet it is written in the current rate of acceleration. The web's beauty lies partly in its impermanence. We live in a rare era when it can be mapped in full when light from the farthest filaments still has time to reach us. The first comprehensive maps of the cosmic web are only a few decades old, yet they already reveal the profound role of dark energy in shaping the long-term destiny of structure. As the expansion continues, the densest knots will remain bound, while the connecting filaments fade, leaving islands of matter adrift in an ever larger sea. The web's geometry is also a measure of the balance between gravity and dark energy. Too much dark energy too early, and the web would never have formed. Too little, and it would grow until collapsing into larger structures. Our universe exists between these extremes, a balance that seems coincidental and yet is essential for the richness we observe. This coincidence, the near equality today of matter and dark energy densities, remains unexplained. The cosmic microwave background provides the initial conditions. Supernova reveal the current acceleration, and the cosmic web shows the evolution in between, each data set reinforcing the same picture. In this interconnected chain of evidence, the web is the middle link translating early fluctuations into present-day structure, under the influence of an accelerating expansion. Observing it requires mapping millions of galaxies each, a tiny point in the grand design, their positions revealing the invisible dark matter that binds them. The largest known structures, such as the Sloan Great Wall, stretch over 1 billion light-years, yet they are still transient on the scale of eternity. As dark energy continues its work, such walls will fragment their parts, carried away beyond any possibility of causal contact. The irony is that the cosmic web, which seems to bind the universe together, is in truth a temporary arrangement on the way to isolation. Its patterns are real and measurable, but their permanence is an illusion born of our short perspective. In the slow view of the cosmos, the web is a passing phase, a snapshot in a much longer process. The filaments that now connect clusters will fade and the great voids will grow until each island of matter is alone. For now, the patterns remain, and in their delicate balance between growth and suppression lies one of the clearest signatures of dark energy's role in shaping the universe. The cosmic web is both a relic of the past and a prophecy of the future, its present form the result of billions of years of interplay between gravity's pull and dark energy's steady push. It is a map not just of where galaxies are, but of the forces that have governed their paths, and in its vast architecture we see the imprint of the invisible. The reluctant clusters hold their ground as long as gravity allows vast assemblies of hundreds or thousands of galaxies bound together by the combined mass of their star's gas and especially dark matter. Within their boundaries, the pull of gravity is strong enough to resist the general expansion of the universe. Galaxies orbit the shared center of mass-hot plasma, fills the space between them, and dark matter forms an extended halo that stretches far beyond the luminous components. The fact is that these clusters are the largest gravitationally bound structures in the cosmos, some spanning 10 million light-years, and containing masses equivalent to 1,000,000 billion suns. Their binding energy prevents them from being torn apart by cosmic expansion, at least for now. A lesser-known detail is that the gas in clusters is heated to tens of millions of degrees and shines brightly in X-rays, making it a critical probe of their total mass through hydrostatic equilibrium. These clusters also act as gravitational lenses, bending the light from more distant galaxies into arcs, and multiple images allowing astronomers to map their dark matter distribution with remarkable precision. Yet even these immense structures cannot escape the influence of dark energy forever. A quiet mystery lies in the subtle balance. The acceleration of the universe's expansion does not pull clusters apart directly, but it prevents new ones from forming and limits the infall of galaxies at their edges. Over billions of years, the background expansion will carry away any galaxies not already bound, and the most distant members of a cluster will eventually drift beyond its gravitational grasp. The first soft irony is that the largest gatherings of galaxies which seem so permanent exist in a brief window of cosmic history when they can still be assembled. The second irony is that while clusters are fortresses of gravity, they are surrounded by an ever-thinning moat of intergalactic space that is deepening with time. The third irony is that the very stability of clusters makes their eventual isolation more absolute. They will remain intact, but with nothing new ever joining them, their role in the cosmic web will fade. Observations show that cluster growth has already slowed compared to earlier epochs, with surveys detecting fewer massive clusters at high redshift than predicted in a universe without dark energy. Simulations confirm that as dark energy dominates, the rate of structure growth approaches zero, freezing the cluster population in place. The analogy of cities on islands captures a fragment of this truth. Trade and migration once flowed freely along bridges of land, but as the sea rises, the islands remain intact while the bridges vanish, leaving each city self-sufficient but cut off. In the far future, clusters will be like these cities, each holding its own internal life while the rest of the universe slips away. The Coma cluster, for example, lies over 300 million light-years from Earth and contains thousands of galaxies, yet its influence reaches only so far. Beyond its edges, the accelerating expansion will eventually carry neighboring structures beyond reach. The Virgo cluster nearer to us is the gravitational center of our local supercluster, and though it binds its members securely now, it too will lose contact with the broader network of galaxies. A subtle detail is that cluster dynamics provide an independent test of cosmology. By measuring the abundance of clusters at different redshifts and comparing it to theoretical predictions, astronomers can constrain both the matter density and the properties of dark energy. The thermal Sunyaev-Zeldovich effect, where hot cluster gas distorts the cosmic microwave background through inverse Compton scattering, offers another way to count clusters across cosmic time. All these methods converge on the same story. Dark energy is real, and it is already shaping the fate of the largest bound systems. The mystery of its origin remains untouched by these observations, but its consequences are unambiguous. As time passes, the boundaries of each cluster will become the limits of the observable universe, for any inhabitants within, because the accelerating expansion will carry all unbound light sources beyond the cosmological event horizon. Inside, life will go on as gravity dictates. Galaxies will orbit, stars will form and die, black holes will merge, and the hot gas will gradually cool. Outside, the rest of the cosmos will fade, not because it has vanished, but because its light can no longer arrive. This slow isolation is already written into the equations that describe the expansion. The irony is that the same dark energy that preserves clusters against the pull of other clusters also ensures that they will never meet again. The local group, including the Milky Way and Andromeda, will one day merge into a single elliptical galaxy, bound together with its few remaining satellites, while more distant companions in Virgo recede into invisibility. The perception of permanence that clusters evoke is thus an illusion born of timescales. They are as transient in the life of the universe as clouds are in the life of the sky, though their dissolutions are measured in trillions of years. In the present we can still map them, still trace the filaments feeding into them, still measure the slow motion of their galaxies with respect to their centers. But the maps will one day be records of a vanished age. The filaments will be broken, and the motions will be confined to smaller and smaller arenas. The reluctant clusters will not resist forever. They will simply endure in place, each a self-contained world in a cosmos of growing emptiness. Their endurance will not be a victory over dark energy, but a coexistence on terms they cannot change. In this balance, the role of dark energy is clear. It does not attack. It does not dismantle it. Simply prevents anything new from joining, allowing gravity to hold what it already has while space takes everything else away. Whispers in the microwave glow arrive from every direction, a faint and ancient light that has travelled across the universe for 13.8 billion years. This is the cosmic microwave background, the cooled remnant of radiation, from a time when the universe was young, hot and dense. It fills all of space with the nearly uniform temperature of about 725 Kelvin, a sea of photons left over from the epoch of recombination, when electrons and protons first combined to form neutral hydrogen, and the cosmos became transparent to radiation. The fact is that this background is not perfectly smooth. It carries minute temperature variations at the level of 1 part in 100,000. These variations are the imprints of primordial sound waves' baryon acoustic oscillations, propagating through the plasma of the early universe, frozen into the radiation when transparency began. A lesser-known detail is that the statistical patterns of these fluctuations, mapped with extraordinary precision by satellites such as COBE WMAP and Planck, reveal not only the geometry of space, but also the relative amounts of matter radiation and dark energy. The positions and heights of the acoustic peaks in the power spectrum are sensitive to the total energy density of the universe, while the overall shape of the spectrum constrains the balance between matter and dark energy at late times. A quiet mystery emerges from these measurements. Although the cosmic microwave background encodes the conditions of the universe only 380,000 years after the Big Bang, its interpretation depends on the accelerated expansion billions of years later. This is because the photons we observe have travelled through the evolving universe, their paths subtly altered by gravitational lensing and the integrated Sachs-Wolf effect, where time-varying gravitational potentials imprint slight changes in the photon's energies. The first soft irony is that the faintest and coldest light in the universe carries some of the most precise information about its larger-scale fate. The second irony is that this relic from the hottest era tells us about the influence of dark energy, which dominates only in the coldest era. The third irony is that while the microwave background is perfectly isotropic to the human eye, it is within its tiny deviations that the story of the universe is most clearly written. These anisotropies form a cosmic map that, when decoded, reveals a universe that is flat to remarkable precision, and composed of about 5% ordinary matter, 25% dark matter, and 70% dark energy. The Planck satellite's final results, for example, constrain the dark energy density parameter to within a few percent, aligning with independent measurements from supernovae and large-scale structure. A subtle detail is that the integrated Sachs-Wolf effect, which is sensitive to the acceleration of the universe, is visible in correlations between the microwave background and the distribution of galaxies at low redshift. This effect occurs because in a universe with dark energy, the gravitational potential wells created by large-scale structures decay over time, causing photons to gain or lose energy as they pass through. Without dark energy, these potentials would remain constant during the matter-dominated era, and the effect would vanish. Observationally detecting this signal requires statistical comparisons between CMB maps and galaxy surveys, and the results provide yet another line of evidence for cosmic acceleration. The analogy of a photograph taken billions of years ago but only now developed captures part of the truth. The microwave background is an image of the infant universe, but the developing process took place in the intervening space-time shaped by expansion, structure growth, and dark energy's steady influence. The photons are not mere messengers of the past. They are also witnesses to the changes along their journey. In this way, the CMB serves as both a starting point and a running logbook of cosmic history. The mystery deepens when considering how the early universe's near-perfect uniformity gave rise to the intricate web of galaxies we see today, and how dark energy's later dominance has frozen that growth on the larger scales. The microwave background holds the seeds of the web's formation, yet it also contains the parameters that dictate its eventual dissolution. The precision of these measurements is unmatched in cosmology. Even tiny shifts in the positions of the acoustic peaks can indicate changes in the equation of state parameter for dark energy, though current results remain consistent with a cosmological constant. Future missions aim to measure the polarization of the CMB on even finer scales, which could further constrain dark energy models by improving our understanding of reionization and gravitational lensing. The irony is that we learn about the universe's accelerating expansion from a light that has been steadily losing energy for nearly 14 billion years, stretched from visible and infrared wavelengths down to millimeter waves. Its photons, each with an energy far less than that of a single visible photon, outnumber every particle of matter in the cosmos, silently filling every cubic centimeter of space. In the grand accounting of the universe's energy budget, this radiation is now negligible, yet in the accounting of a knowledge it is priceless. The CMB does not shout its message. It whispers in patterns that must be teased out with statistical tools and careful modelling. The uniform glow is the canvas, the anisotropies are the brush strokes, the interpretation is the gallery in which we finally see the whole picture. In that picture, dark energy is unavoidable and invisible presence, whose effects are woven into both the past and the future. The photons arriving now from the surface of last scattering will be followed in trillions of years by others that have traversed an ever emptier universe, their wavelengths stretch so far they will be undetectable. Long before that time, the microwave background will fade beyond any conceivable instrument, leaving no trace of the early universe for the astronomers of that future to find. We live then in a privileged moment, when the whispers in the microwave glow can still be heard, when they can still confirm the accelerating expansion and the role of dark energy in shaping cosmic history. For now they remain our oldest and most reliable record, a quiet chorus from the first light carrying through the darkness the parameters that define everything. The equation of state is the quiet mathematical phrase that describes how a form of energy relates its pressure to its density, and for dark energy it is written as W, the ratio of pressure to energy density. In the simplest model, corresponding to a cosmological constant W equals -1 exactly. This means that the pressure is negative and equal in magnitude to the energy density, producing a repulsive effect on cosmic scales that drives the acceleration of expansion. The fact is that current observations from multiple independent probes, supernova distances, cosmic microwave background anisotropies, and large-scale structure measurements all find W to be very close to -1 with no significant sign of deviation. This supports the interpretation of dark energy as vacuum energy, a constant property of space itself. A lesser-known detail is that small deviations from -1 are still possible within observational uncertainties, leaving open the possibility of more dynamic forms of dark energy, such as quintessence, where W changes slowly with time. In such models, dark energy is not a fixed feature of the vacuum, but a slowly evolving scalar field, its energy density diluting differently from matter or radiation. A quiet mystery lies in why you should be so close to -1 now during an epoch when matter and dark energy have comparable densities, a condition that is fleeting on cosmological timescales. The first soft irony is that this single parameter distilled from vast amounts of data can dictate the long-term fate of the universe. The second irony is that while W appears simple in form, it may conceal deep complexity about the nature of space and the laws of physics. The third irony is that the value we measure today may not be the value the universe has always had, but we have only a snapshot from our particular cosmic time. Determining W with greater precision is a central goal of observational cosmology. Surveys such as the Dark Energy Survey, the Kilo Degree Survey, and future missions like the Nancy Grace Roman Space Telescope and Euclid are designed to refine this measurement by mapping the expansion history and growth of structure with unprecedented detail. They use a range of complementary techniques including weak gravitational lensing, galaxy clustering, and more distant supernovae to constrain W and its possible evolution. A subtle detail is that the growth rate of cosmic structure is sensitive to W in a way that is different from distance measurements. So combining these methods breaks degeneracies between parameters and tests, general relativity itself. In some parameterizations, W is expressed as W0 plus way times 1 minus, the scale factor, allowing a simple model of its variation with time. Current constraints show no significant departure from a constant value, but the error bars leave room for surprise. The analogy of a thermostat set precisely at one temperature, yet potentially adjustable, captures part of the truth. The cosmic thermostat seems fixed at -1, but the possibility that it could drift is not entirely excluded. If W is exactly -1, the future is a steadily accelerating expansion leading to a cold, empty universe. If it is greater than -1, dark energy's influence would weaken over time. If it is less than -1 in what is called phantom energy, the acceleration would grow without bound potentially ending in a big rip, where even bound structures are torn apart. The mystery is whether the universe is telling us a simple story about a constant vacuum energy, or a more complex one about a changing field. Observationally, the integrated Sachs-Wolf effect, baryon acoustic oscillations and cluster abundance evolution all contribute to Liu's measurement, and each must be modelled with care to avoid systematic errors. The precision required is demanding. Even a small shift in W by a few % can significantly alter the predicted future of the cosmos. In the interplay between theory and data, W acts as a hinge. It connects the abstract equations of cosmology to the tangible observations of the sky. The irony is that our entire understanding of dark energy's physical nature may rest on distinguishing whether W is -1 or not, a task that involves mapping billions of light-years of space and billions of years of time to refine a single number. For now, the evidence is consistent with the simplest case, and the cosmological constant remains the prevailing explanation. Yet the possibility of change keeps the field alive with anticipation. If future measurements detect a shift in WW, it would signal new physics beyond the cosmological constant, perhaps a dynamic field with interactions we have yet to imagine. Until then, W sits at -1 like a perfect balance point, the pressure and density in exact opposition, creating a steady acceleration that neither strengthens nor weakens. The calmness of this result belies its profound consequence. It means that the universe's large-scale expansion is not evolving in its acceleration rate, at least not in a detectable way. This steady behavior is in stark contrast to the universe's earlier epochs, when radiation or matter dominated and the expansion decelerated. In that contrast lies another irony, that the current acceleration is not a transient fluctuation, but an enduring condition that will shape the cosmos for as far ahead as we can calculate. If W truly remains fixed at -1, then in the far future the observable universe will shrink in scope, not because it is physically contracting, but because the event horizon will limit the regions from which light can ever reach us. Galaxies not bound to our own will fade beyond detection, and the universe will appear emptier and darker with each passing billion years. All of this rests on a number that fits neatly into the field equations of general relativity, a number that has no units and no direct physical manifestation yet, which defines the destiny of everything on the larger scales. The equation of state is thus both a precise scientific tool and a quiet philosophical marker, reminding us that the ultimate structure of reality can sometimes be encapsulated in the simplest ratios. For now remains as close to -1 as we can measure, and in that closeness lies the ongoing steady hand of dark energy stretching space, with the gentlest yet most relentless touch imaginable. Quintessence is the name given to a class of models in which dark energy is not a fixed property of space, but a dynamic field that evolves over time with its pressure-to-density ratio WW differing from -1 and potentially changing as the universe ages. In these models, the field behaves somewhat like the inflaton field thought to have driven inflation in the early universe, but with a much lower energy scale and acting over vastly longer timescales. The fact is that such a field could in principle explain why dark energy's density is of the same order as the matter density today, without invoking coincidence if its evolution naturally slows to a value that dominates only in the current epoch. A lesser-known detail is that quintessence fields are often modelled with potentials that allow tracker solutions, where the field's evolution converges toward a common behaviour regardless of initial conditions. This property makes them appealing as a way to avoid fine-tuning, but it also constrains them tightly because any viable model must match the observed acceleration history as measured by supernovae, the cosmic microwave background and large-scale structure. A quiet mystery lies in whether any realistic physical field can play this role without conflicting with other constraints from particle physics and early universe cosmology. The first soft irony is that the very name quintessence, drawn from the ancient concept of a fifth element, invokes an idea once used to explain celestial perfection, yet here it is used to describe something we cannot see or touch, whose imperfection in constancy is its defining trait. The second irony is that even if quintessence exists, it may be observationally indistinguishable from a cosmological constant for most of cosmic history, revealing its difference only in the deep future or in the subtle details of early structure growth. The third irony is that by trying to make dark energy more dynamic, and thus perhaps more understandable, quintessence introduces more degrees of freedom, potentially making the problem harder rather than simpler. Observationally searching for quintessence involves looking for deviations of W from -1, and for any time dependence in that parameter. This can be done by measuring distances and expansion rates across a wide range of redshifts, combining supernova data with baryon acoustic oscillations and weak gravitational lensing to reconstruct the history of cosmic acceleration. If W is found to vary, it would break the simple symmetry of the cosmological constant and force a re-evaluation of the underlying physics of dark energy. A subtle detail is that quintessence fields typically have an equation of state parameter greater than -1, so their energy density decreases slowly over time rather than remaining constant. This would mean that in the far future their influence would diminish, potentially allowing the expansion rate to asymptotically approach a constant rather than accelerating forever. More exotic models such as phantom energy have W less than -1, leading to a future in which acceleration grows without bound and the universe ends in a big rip. Between these extremes lie many possibilities, from thawing models, where the field has been nearly frozen and is just beginning to evolve, to freezing models where it has been evolving and is now slowing toward a constant value. The analogy of a landscape with valleys and hills is often used. The quintessence field rolls slowly down a potential, its speed determining W, and the shape of the potential determining whether it will settle into a minimum, keep rolling indefinitely, or change direction. This analogy, though simplified, captures the essential feature that quintessence has dynamics, unlike the fixed energy density of a cosmological constant. The mystery deepens when considering how such a field would interact or not with ordinary matter and radiation. Most models assume these interactions are negligible to avoid conflicts with laboratory and solar system tests of gravity, but in principle, the field could couple weakly, leading to subtle variations in fundamental constants over time. No such variations have been convincingly observed, placing strong limits on any coupling. Quintessence also raises questions about initial conditions in the early universe. If the field existed during inflation or the radiation-dominated era, it must have been subdominant enough not to disturb nucleosynthesis, recombination, or structure formation in ways that conflict with observation. Yet despite these constraints, theorists continue to explore quintessence, because it offers a path to explaining why cosmic acceleration began only recently, rather than being a fixed property of space from the beginning. The irony is that our current measurements of W are consistent with -1 to within a few percent, making it difficult to justify the complexity of quintessence unless future observations reveal a deviation. If such a deviation were found, it would be revolutionary, signaling that the acceleration of the universe is not a static phenomenon, but part of a longer and perhaps more intricate story. The search for this signal is ongoing, with new surveys mapping galaxies, measuring lensing distortions, and capturing more distant supernova to tighten the bounds on W and its rate of change. In the meantime, quintessence remains a possibility, a reminder that our understanding of dark energy is not yet complete and may require new physics beyond the cosmological constant. Whether it proves true or not, the idea has already deepened the dialogue between cosmology and fundamental physics, forcing each to consider scenarios in which the vacuum is not a fixed backdrop, but an evolving participant in cosmic history. In such a picture, the acceleration we observe today is just one phase in a sequence, with past and future epochs potentially behaving differently. For now, the observations we have tell a simple story that fits the cosmological constant well, but the models of quintessence wait in the background like unplayed notes in a score, ready to alter the melody if the next measurement demands it. Until that moment, the universe continues its steady expansion, and the possibility of quintessence remains one of the many ways we try to describe the invisible hand that shapes it. Distances that drift apart are the simplest visual impression of the expanding universe, yet the rate at which they change has become one of the most debated topics in modern cosmology. This rate is expressed by the Hubble constant, which describes the present-day relationship between the recessional velocity of galaxies and their distance from us. In principle, the concept is straightforward: measure how fast a galaxy is receding, measure how far away it is, and divide one by the other. In practice, the measurements are complex and the results depend on the method used. The fact is that two leading techniques currently give values for the Hubble constant that differ by several kilometers per second per megaparsec, a tension that has persisted and even sharpened with improved precision. The first method uses the local distance ladder building from direct measurements of nearby stars via parallax, then to Cepheid variable stars in nearby galaxies, and then to Type Ia supernovae in more distant galaxies. This approach, refined by the supernovae and Hubble constant for the equation of state collaboration, yields a value of about 73 kilometers per second per megaparsec. The second method infers the Hubble constant from observations of the cosmic microwave background by the Planck satellite, which measures parameters of the early universe, and uses the standard cosmological model to extrapolate to the present, giving a value of about 67 kilometers per second per megaparsec. A lesser-known detail is that this difference is larger than can be explained by statistical error in either method, suggesting the possibility of unknown systematics or new physics beyond the standard lambda cold dark matter model. A quiet mystery thus lies in whether the tension is a sign of subtle observational biases or whether it hints at phenomena such as early dark energy, modified gravity, or other departures from the simplest model. The first soft irony is that the universe's expansion rate is in concept one of the most basic cosmological quantities, yet its precise value is among the hardest to pin down. The second irony is that the very methods that give us our most reliable distance measurements also expose the disagreement most clearly. The third irony is that both values are consistent with an accelerating universe dominated by dark energy, yet their difference may be the clue to understanding dark energy's nature more deeply. The Hubble constant is not itself a measure of acceleration, but it anchors the expansion history. Changes in its inferred value can shift the inferred age of the universe and alter the timeline of cosmic evolution. Local measurements rely on the brightness and periodicity of Cepheid variable stars calibrated with geometric distances from parallax as measured by satellites such as Gaia. These calibrations are then applied to supernovae whose brightness yields distances far beyond the reach of Cepheids alone. This ladder has multiple rungs and each must be precise to avoid propagating errors upward. Meanwhile, the cosmic microwave background method bypasses the local ladder entirely, using the sound horizon at recombination as a standard ruler and fitting the data with a cosmological model to project forward to today. Both methods are internally consistent, yet they arrive at different present-day expansion rates. A subtle detail is that other independent approaches such as strong gravitational lensing time delays water-mayor galaxy distances, and the tip of the red giant branch stars generally fall between the two values, but not enough to eliminate the tension. The analogy of two watches set long ago and checked now against the same clock captures part of the situation. Both agree the clock is running, but they disagree on the exact second. In cosmology, that second translates to billions of years in the universe's inferred age, and could reflect a missing piece in our understanding. If the higher local value is correct, the universe would be younger than the standard model predicts from the cosmic microwave background data. If the lower Planck value is right, the local measurements must contain an unrecognized bias. The mystery is deepened by the fact that adjustments to known physics, such as adding extra relativistic particles in the early universe, can bring the two values closer together, but often at the cost of creating other tensions with data. Some proposals invoke an episode of early dark energy, briefly dominant before recombination, which would alter the sound horizon and allow the Planck data to yield a higher Hubble constant without changing the local measurements. Others suggest that systematic errors in Cepheid photometry or supernova calibration might be underestimated, though the teams involved have worked extensively to minimize such effects. For now, the tension stands as one of the few places where precision cosmology might be pointing toward new physics. The irony is that this disagreement, while small in percentage terms, is large in its implications. Resolving it could either reinforce the standard model or force a rethinking of our assumptions about cosmic history. Dark energy's role in this discussion is indirect but critical because the expansion rate today is one of the boundary conditions that any model of dark energy must satisfy. If the Hubble constant is higher, then dark energy's influence must have become dominant slightly earlier. If lower, then the onset of acceleration could have been delayed. Either way, the drift of distances today is the accumulated result of the universe's entire expansion history, shaped in its later stages by the balance between matter's slowing pull and dark energy's steady push. In a sense, the Hubble constant is the present-day note in a symphony that began with the Big Bang and has been playing ever since with dark energy, composing the final lingering movements. The precise pitch of that note remains under debate, and the outcome will shape how we interpret every other observation of the cosmos. For now, distances continue to drift apart at a rate we can measure to a few percent, yet not agree upon exactly leaving the door open to both refinement of our tools and expansion of our theories. Acceleration without touch is one of the strangest features of dark energy, for it works everywhere and on everything without direct contact, without a medium, and without a surface upon which to push. In the language of general relativity, it is not a force in the traditional sense, but a property of space-time itself, altering the metric that defines distances and durations. As the universe expands, dark energy acts to change the rate of that expansion, not by applying pressure in a way that can be felt locally, but by determining the large-scale geometry and evolution of the cosmos. The fact is that no bound system, whether an atom, a planet, or a galaxy, feels this acceleration directly. Within such systems, the local gravitational, electromagnetic, and nuclear forces are far stronger and hold matter together against the background expansion. Only over intergalactic distances where gravity's binding influence weakens and nothing else exerts a counteracting pull does the effect of dark energy become measurable. A lesser-known detail is that the mathematics of this phenomenon can be written in the Friedmann equations, where a term corresponding to a cosmological constant or other dark energy component appears with negative pressure, changing the sign of the acceleration. It is this negative pressure rather than any mechanical push that causes the expansion rate to increase. A quiet mystery lies in why the energy density of dark energy remains constant or nearly constant over time, even as the universe grows. In a cosmological constant interpretation, as space expands, more vacuum energy comes into existence in perfect proportion to the increase in volume, ensuring its density does not dilute like matter or radiation. The first soft irony is that dark energy is most powerful where there is the least to act upon. The emptier the space, the more its influence becomes apparent. The second irony is that it produces a cosmic acceleration without accelerating any particular object in the way we ordinarily use the term. The third irony is that its action is global, shaping the history of the universe as a whole, yet it is invisible and intangible on any local scale. Observationally, this absence of local effect means that detecting dark energy requires measuring the universe itself as the laboratory using light from distant galaxies, the structure of the cosmic web, and the imprint of the cosmic microwave background as test particles in an experiment too large to build by hand. The analogy of a fabric that stretches uniformly at every point comes close. A grid of dots on a rubber sheet moves apart as the sheet is pulled, not because the dots move themselves, but because the space between them increases. In reality, however, space is not a material and is not pulled from any external place. Its expansion is an intrinsic feature of the solution to Einstein's equations when dark energy is present. A subtle detail is that the acceleration's effect can be seen in how the light from distant objects is redshifted more than it would be in a decelerating universe. The precise relationship between redshift and distance measured by standard candles and standard rulers encodes the influence of dark energy on the expansion rate. Without such measurements, we would have no evidence for acceleration, because locally nothing appears to change. The mystery deepens when considering why the influence of dark energy has become significant only in the last few billion years, after the universe spent most of its history dominated first by radiation and then by matter. This so-called coincidence problem has no widely accepted solution. It seems improbable that our cosmic epoch just happens to be the one when dark energy's density is comparable to that of matter. In some dynamic models, the acceleration is a temporary phase, with dark energy's density eventually changing. But in the cosmological constant model, it will continue forever. In either case, the lack of direct interaction between dark energy and matter makes it uniquely difficult to study, for it leaves no laboratory-scale signatures, no particles we can catch, no fields we can measure directly. The irony is that we know it exists not because we can see or feel it, but because the equations that describe the universe's expansion require it to match observations. It is an actor that moves the stage rather than the players, yet without its presence the play's progression would be entirely different. Measurements of the integrated Sachs-Wolf effect, baryon acoustic oscillations and the growth rate of structure all confirm its role, but none offer a handle on its substance. It could be an inherent feature of space-time or the effect of an unseen field, but in either case it exerts influence without the exchange of momentum in the ordinary sense. This absence of touch leads to another subtlety. The principle of equivalence in general relativity means that all forms of energy and momentum affect the curvature of space-time, but dark energy is distinguished by having a uniform density and negative pressure, producing a curvature that manifests as accelerated expansion rather than gravitational attraction. In the far future, this touchless acceleration will leave each bound system in an island of darkness separated from all others by an ever-expanding void. Within each island, life and motion will continue according to local rules, but the larger universe will fade from view, not because it has ended, but because it has receded beyond the horizon, defined by the speed of light in an accelerating space. This is the paradox of acceleration without touch. It changes the fate of everything, without changing the nature of anything it passes through. Its power is absolute on the grandest scales and absent on the smallest, a duality that makes it both the most and the least intrusive feature of the cosmos. It is not a wind that pushes the galaxies away. It is the steady unfolding of the geometry that defines the distances between them. In the quiet unfolding of this geometry, dark energy continues its work unseen yet unmistakable, the hand that never touches, and the force that never pushes, yet the reason why the universe grows faster with each passing billion years. The future horizon is not a physical wall, yet it will one day define the limits of everything that can be seen, the boundary beyond which no new light will ever arrive. In a universe dominated by dark energy, this horizon is the natural consequence of accelerated expansion, a curved line in space-time beyond which events can never influence us no matter how much time passes. The fact is that as the acceleration continues, galaxies not gravitationally bound to our own will recede at such a rate that the light they emit will never overcome the stretching of space to reach us. They will not suddenly vanish. Instead, they will grow dimmer and redder over billions of years. Their light shifted to longer and longer wavelengths until it fades entirely beyond detectability. A lesser-known detail is that this cosmic event horizon is different from the particle horizon, which marks the limit of what we can see today, based on the finite age of the universe. The particle horizon will continue to grow as light from more distant regions arrives, but the event horizon will remain fixed in moving coordinates defining a finite volume of space-time from which signals can ever be received. A quiet mystery lies in the thought that much of the universe we can see today is already beyond this event horizon, meaning that the light now reaching us left its source billions of years ago, and no new light from that same source will ever arrive. The first soft irony is that the most distant galaxies we see are not on their way to being hidden. They're already cut off their final messages en route, even as we observe them. The second irony is that while the horizon is defined by acceleration on the grandest scales, it is invisible and leaves no trace in the local geometry. Space feels no different here than it does there. The third irony is that the galaxies disappearing from view are not slowing down or being swallowed. They are simply carried away by the expansion of the very space between us and them. The physics of this process can be described by considering how the recession velocity of an object increases with distance in an expanding universe. In a universe with constant dark energy density, the expansion rate asymptotically approaches a fixed value, leading to a fixed event horizon radius of about 16 billion light-years in proper distance. Any galaxy farther than this will never send light that can reach us in the future, regardless of how long we wait. Observations today show that the expansion rate is already close to this asymptotic behavior, meaning the shape of the future horizon is largely set. A subtle detail is that the presence of a horizon has implications for quantum fields in curved space-time, leading to effects similar to those near black holes, such as a small associated temperature, though far too low to be of practical consequence. The analogy of being on a ship in an infinite ocean captures a fragment of the truth the water stretches endlessly in every direction, but the swell of the sea moves such that there is a circle beyond which no wave or vessel can ever approach, even though the sea itself has no wall. In this ocean, the currents are not water flowing, but the expansion of space itself, and the horizon is simply the point beyond which the currents outpace any signal trying to move inward. The mystery deepens when we consider that the observable universe will grow emptier, not because galaxies have moved into some separate realm, but because the light connecting us to them has been severed by the expansion. Within a few trillion years, even the nearest clusters outside the local group will fade from sight, leaving only our gravitationally bound companions. The cosmic microwave background, which now fills the sky with a faint cold glow, will be stretched to such long wavelengths that it will become undetectable, erasing our most ancient window into the early universe. Future observers, if any remain, will see only their local group of stars and the dark between them, with no evidence of the larger cosmos beyond. The irony is that we live in an era rich in information about the universe, precisely because the horizon has not yet contracted around us. We can still see billions of galaxies, measure their distribution, and read in their light the history of expansion and acceleration. In the far future, the same physical laws will apply, but the evidence will be gone. The shrinking of the visible universe is not a catastrophe in the traditional sense. It happens slowly, almost imperceptibly on human timescales. Yet over cosmic time, it transforms the universe from a vast connected web into a collection of isolated islands. Within each island, gravity will maintain its bonds, but beyond everything will fade into darkness. This outcome is unavoidable in a universe with unchanging dark energy density and an accelerating expansion. If dark energy's nature changes, if its equation of state shifts, the future horizon could alter in size or even vanish if acceleration were to cease. But all current evidence points toward a steady or nearly steady acceleration, fixing the horizon and sealing the fate of most of the cosmos to disappear from view. Even knowing this, the concept remains counterintuitive. The galaxies are not moving through space faster than light. Rather, the space between us and them is expanding in such a way that their light can never close the gap. In the equations of general relativity, this is entirely consistent with the speed of light, as a limit for the limit applies locally, while global expansion is a change in the metric itself. Thus, the horizon is a feature not of speed but of geometry. In the present, we can still chart the galaxies near the edge of visibility, still measure the faint light from those already beyond the event horizon, but whose last photons are only now arriving. Each observation is a farewell, a final contact before the universe's expansion severs the connection forever. In this way, the future horizon is not just a boundary in space, but a boundary in time, the edge of all possible communication with the rest of the cosmos. It is the inevitable product of acceleration without touch, a line that closes slowly yet inexorably, leaving each surviving island of matter alone in an ever-growing void. A universe without witnesses is the quiet destination toward which cosmic acceleration carries us, a state where the vast structures we now observe have passed beyond the reach of light, and the night sky has grown sparsely populated. In such a future, the local group, having merged into a single massive galaxy over billions of years, will be surrounded by emptiness. The fact is that in a universe dominated by dark energy, only gravitationally bound systems can remain together. Everything else will cross the event horizon, its light forever unable to reach us. This process will not be dramatic on human timescales. The disappearance of galaxies will be so gradual that countless generations could live and die without noticing any change, yet over hundreds of billions of years the effect will be complete. A lesser-known detail is that the night sky's transformation will be asymmetrical in time. The rich tapestry of galaxies and clusters will persist for many billions of years before fading, but once they are gone, they can never return. A quiet mystery lies in whether any civilization existing far in the future and confined to a single bound system could ever deduce the true nature of the universe without access to the observational evidence we have today. The first soft irony is that our own epoch, filled with accessible clues about the Big Bang cosmic expansion, and dark energy is a temporary condition in cosmic history. The second irony is that the very acceleration that allows the universe to persist indefinitely in time also hides most of it from view. The third irony is that as the observable universe shrinks, the physics governing it will remain unchanged, but the context needed to understand those laws will vanish. In the distant future, the cosmic microwave background will be so stretched in wavelength that it will be undetectable even with instruments larger than planets, its photons diluted to energies so small they merge with the random noise of the local environment. The galaxies we now see at great distances will have receded so far that their light will be frozen just short of the horizon, never able to cross into the realm of possible detection. The only stars visible will be those bound within the merged remnant of the local group. A subtle detail is that even the nearest large structure beyond our group, the Virgo cluster, will eventually be lost its light, unable to overcome the expansion of space. This isolation will not come with any boundary or wall. The space beyond will still exist, but it will be empty of information. The analogy of living on an island whose surrounding ocean has grown so vast that all other shores have fallen permanently below the horizon captures part of this fate, though the cosmic version involves no curvature of the surface, only the quiet acceleration of the distance itself. For observers in that far-off time, cosmology as we know it will be impossible. Without evidence of other galaxies, without the microwave background, Without the redshift-distance relationship, there will be no empirical path to discovering that the universe had a hot dense origin, or that it has been expanding for over 10 billion years. The mystery of the universe's beginnings and its large-scale structure will be beyond recovery, not because the knowledge has been erased, but because the signs have been carried away. Even if those future observers possess the same physical laws, we know now the lack of large-scale context will obscure the most fundamental facts about the cosmos. The irony is that our current ability to study and understand the universe's vastness is a privilege of timing, not inevitability. We're alive during the brief window when the evidence is both abundant and accessible, before acceleration has erased it from view. This window is not a matter of millions of years, but billions long by human reckoning, yet fleeting on cosmic scales. In that sense, a universe without witnesses is not a change in the cosmos itself, but in the portion of it that any given observer can know. The expansion will continue, stars will be born and die within the bound system planets will orbit, and local gravitational dynamics will unfold as always. What will be missing is the connection to the greater whole, the awareness that one galaxy is but a single island in an immeasurable archipelago. In such isolation, the night sky will still hold stars, but they will all belong to the same merged galaxy, and their arrangement will speak only of local history. The deep faint smudge of the Andromeda galaxy, which in our time is a familiar feature to those who seek it out, will long since have merged with the Milky Way, leaving no external marker of the wider universe. Without the contrast of the far away, the near will seem like the whole. A subtle detail is that while gravity binds the stars and dark matter within the island galaxy, the intergalactic medium between the islands will cool and rarefy to the point of near non-existence, a vacuum even more perfect than the one we measure today. In the darkness beyond the galaxy's halo, space will still expand indifferent to the bonds that hold the local system together. In this way, the universe without witnesses will not be empty in an absolute sense, but it will be observationally empty for those confined to a single gravitational domain. For any mind or instrument in that time, the cosmos will appear finite, self-contained, and static, even though in reality it will still be infinite, expanding and evolving beyond the horizon. The paradox is that acceleration will have preserved the galaxy by keeping external threats eternally out of reach, yet it will also have cut it off from the truth of its origin. This is the silence that dark energy brings, not a silence of sound, but of information, a slow and irreversible narrowing of what can be known. Today we can still listen to the universe speak in the light of distant galaxies and in the faint echoes of its first moments, but in the future those voices will fade and the night will hold only the local chorus, unaware that it was ever part of a grander song. Endings without edges describe a universe that will never collapse into a final singularity, never halt its expansion, and never arrive at a moment that can be called an absolute end. In a cosmos dominated by dark energy, with a constant density and an equation of state parameter equal to -1, the expansion will continue forever, growing ever closer to a steady exponential pace. The fact is that this fate is known as the heat death, or the big freeze, a condition in which the universe becomes colder, darker, and more dilute over unimaginable spans of time. Stars will exhaust their fuel, galaxies will fade, and the last traces of structure will be reduced to isolated remnants floating in an ever-expanding void. A lesser-known detail is that in this scenario the accelerated expansion ensures that all regions not bound by gravity will eventually move beyond each other's event horizons, so that any exchange of matter, light, or information will become impossible. The isolation will deepen until each gravitationally bound system is alone, surrounded by an unchanging blackness. A quiet mystery lies in the thought that while this future seems empty and static, the expansion of space will still continue without interruption, a silent process with no perceptible effect on anything within the isolated systems themselves. The first soft irony is that the universe will go on existing without limit in time, yet all events within it will slow and fade until change becomes imperceptible. The second irony is that the process that prevents a final collapse also prevents the renewal of large-scale complexity. The third irony is that infinity in duration will coincide with near emptiness in content. Over time, the main sequence stars will all burn out, leaving behind white dwarfs, neutron stars, and black holes. The white dwarfs will cool to black dwarfs, their thermal energy radiated away over quadrillions of years. Neutron stars will remain inert, slowly losing rotational energy, while black holes will dominate the mass of each surviving galaxy remnant. In the far future, even these black holes will begin to evaporate through Hawking radiation, shrinking over time until they disappear, entirely releasing their last energy as a faint burst of particles and radiation. A subtle detail is that the timescales for these processes are so vast, on the order of 10 to the power of 100 years, for the largest black holes, that they dwarf the current age of the universe by factors beyond ordinary comprehension. The analogy of an ancient city slowly emptied of its inhabitants, its buildings eroded to dust, and the dust dispersed into the wind captures some of the feeling of this fate, though here the city is the cosmos, and the wind is the expansion of space itself. The mystery deepens when considering whether dark energy will remain constant forever. If it evolves toward a less negative equation of state, the acceleration could slow, altering this picture. If it becomes more negative, entering the phantom energy regime, the expansion could tear apart even bound structures in a catastrophic big rip. But all current observations suggest a stable cosmological constant, and thus a slow drift toward eternal isolation and low energy. In this projection, after the last black holes evaporate, the universe will be filled only with extremely low-energy photons, neutrinos, and other particles, their wavelengths stretched to sizes greater than the observable universe today. No structures will remain, no temperature gradients will persist, and no process will be possible to extract usable energy. Time will continue to pass, but with no change to mark its flow. The irony is that in such a future the universe will be as close to absolute stillness as it can be, yet it will never stop expanding. Even without edges, it will continue to grow in size, with every region endlessly beyond reach of every other. The concept of an ending without a final moment challenges human intuition, which expects conclusions to be marked by discrete events. Instead, this end is an approach to a limit that can never be reached, a fading into an infinite continuation. The observable universe will shrink to encompass only what is bound together locally, but the actual universe will keep expanding without bound. In this sense, the edges disappear, not because they move outward faster than light, but because there is no longer any way to define them within a horizon that holds nothing new. For now we live in an age where the universe is rich in light and structure, where galaxies interact and form new stars, where the cosmic microwave background still carries the imprint of the beginning. But this is only one chapter in a much longer book, a chapter that will eventually give way to a sparse and quiet final act without conclusion. The cosmos will not collapse, nor will it stop. It will simply continue, each moment indistinguishable from the last, each horizon empty of anything unfamiliar. The phrase "endings without edges" is thus not a poetic exaggeration, but a literal description of the far future implied by our current measurements of dark energy. It is the infinite continuation of a process that has no goal and no final state beyond the dissipation of all complexity. The structure we see now, from galaxy clusters to cosmic filaments, is temporary. The smooth, nearly featureless expanse is the lasting reality. This knowledge carries its own quiet beauty, for it shows that the universe is not a stage built for a single performance, but an ever-changing geometry that eventually becomes a pure unadorned space. In that unadorned space there will be no edges to cross and no endings to witness, only the continuation of the expansion into a future without boundaries and without return. The faintest breath of time belongs to the farthest reaches of the universe's future, an age so distant that every familiar measure has lost its scale. In the endless expansion driven by dark energy, clocks still tick, but their intervals stretch in meaning, for there is almost nothing left to mark their passage. The fact is that as the universe approaches a state of near emptiness, all remaining processes slow. Interactions between particles become vanishingly rare, the density of radiation falls towards zero, and even the decay of the last structures such as black holes proceeds on timescales so long they seem frozen. A lesser-known detail is that the acceleration of the universe alters the relationship between time and distance, for any observer making the far future a place where most of the cosmos is not merely unseen, but causally disconnected. In this realm, time is still infinite, yet the number of distinguishable events within it dwindles to almost nothing. A quiet mystery lies in whether time has meaning when there is no change to measure it against, when every moment is identical in content to every other. The first soft irony is that dark energy, which once shaped the growth of galaxies and set the cosmic web in motion, will in this distant future serve only to preserve an expansion that has nothing left to separate. The second irony is that the universe's vastness will continue to grow while the amount of activity within it approaches zero. The third irony is that the very persistence of time ensures that its emptiness will also persist forever. The cosmic event horizon, already fixed in scale by the constant acceleration, will define a permanent boundary around each isolated remnant of matter. Beyond it, other remnants will also persist unreachable and unobservable. Within each horizon, local time will proceed according to the motions of whatever remains bound, perhaps long-cooled stellar remnants in slow orbits, perhaps the occasional gravitational wave from a black hole merger in the final stages of evaporation, but these will grow increasingly infrequent until they too are gone. A subtle detail is that quantum effects such as the evaporation of black holes are the last engines of change in such a universe, producing faint trickles of particles that disperse irreversibly into the void. When the final black hole disappears, there will be no structures left to alter the surrounding space-time, only a thin sea of photons, neutrinos, and other light particles stretched across a horizon that can no longer deliver anything new. The analogy of breathing into an infinite cavern comes close. The first breaths echo their sound, bouncing off walls that still lie within reach, but eventually the echoes fade and each breath seems swallowed by silence that never answers back. In the cosmic version, the breaths are the final events, and the silence is the unchanging geometry of accelerated expansion. The mystery deepens when one considers whether the concept of future retains meaning without novelty. For any intelligence existing in this remote era, the sense of history would be absent, for nothing would happen that could be distinguished from anything before it. Time would still exist as a parameter in the equations of physics, but it would no longer have narrative. The faintest breath of time is thus not simply the smallest increment, but the point at which increments themselves lose significance. Dark energy ensures that this state is not reached suddenly, but approached asymptotically over a span so long that its arrival is never marked. Yet, in its inevitability, there is a kind of completeness. The expansion has fulfilled itself, spreading the universe so thin that even light cannot cross the distances between the last survivors. For now, the universe is still rich with motion and structure. Stars burn, galaxies collide, clusters form, and light travels freely across billions of light years. But these are all features of an early phase, a time when the breath of change is still deep and regular. As dark energy continues its unrelenting influence, each cycle of creation and destruction will grow slower and rarer, until what remains is not a final event but a final condition. The irony is that while the faintest breath of time will be the smallest possible measure of change, it will last forever, repeating itself endlessly without variation. The expansion will not stop, the horizons will not shrink, and the emptiness will not fill. This is not an ending in the sense of a conclusion, but the arrival at a state where nothing follows except more of itself. In this perspective, the universe is not a story with a beginning, middle, and end, but a process that, once set in motion, proceeds through stages of richness and complexity, before settling into a form so minimal that its continuation is indistinguishable from stillness. The faintest breath of time is the point at which the fabric of space continues to stretch, yet there is no longer any motion within it to bear witness. It is a silence deeper than absence, for absence still implies something missing while this silence is complete in itself. In contemplating this, we are reminded that the universe's future is not shaped by drama or finality, but by the same quiet persistence that governs its present dark energy, steady and unchanging, guiding the expansion toward a state that will last without limit. The universe drifts onward, its expansion slow and steady to the human mind, yet relentless across the ages. In the present, light still arrives from distant galaxies carrying the quiet record of their shapes and motions. Stars still burn, planets still orbit, and the cosmic web still traces its immense filaments across the dark. But in the far stretches ahead, the light will thin, the structures will fade, and the horizon will close. There will be no sudden moment, no final sound, only the gradual passing of what is now into what will always be. Dark energy will remain unchanged and untiring, holding the same influence it has held since it first began to dominate. Space will go on stretching, making more room for the emptiness between the last islands of matter. Those islands will remain bound slow in their orbits long after the last new light has crossed the void between them, and beyond their edges nothing new will ever come. Time will continue, yet it will carry almost nothing with it, only the repetition of stillness. This is not an ending in any ordinary sense. It is the settling of the cosmos into a state so constant it becomes a kind of rest, the whole of existence at ease in its own expanse. The patterns of today will be gone, but the space that held them will endure wider than thought, softer than silence, and in that silence there will be no need for measure, for change, or for memory. The breath of time will be faint, but it will never cease.